Good evening. I'm Helen Houghton. It is my pleasure to welcome you to tonight's lecture, The Brain as a Metaphor-Making Machine, by Michael Salcman, followed by a brief interview with Linda Dawn and then Q&A at the very end. But in addition to being a widely published and prize-winning poet of 5 collections of poetry, as well as editor of 3 anthologies, including Poetry in Medicine, an anthology of poems about doctors, patients, illness, and healing, Michael is an art critic and an internationally known neurological surgeon, former president of the Congress of Neurological Surgeons, and author of nearly 200 medical and scientific texts, and author or editor of several medical scientific books. By way of background, he was born in Pilsen, Czechoslovakia in 1946, the son of Holocaust survivors, and he came to the United States in 1949. At age 16, he attended Boston University and received a BA and an MD, and graduating first in his class at age 22. After a residency in neurological surgery at Columbia University, he began his career at the University of Maryland School of Medicine, and in 1984 was appointed the youngest chairman of neurosurgery in the United States. His clinical research focused on diseases of the brain. He was a pioneer in the treatment of malignant tumors and has been honored as distinguished alumnus of Columbia's Neurological Institute and of Boston University's School of Medicine. Michael's passion for poetry and art, combined with his neurological expertise, have led him to write and lecture widely on the subject we'll hear about tonight. Linda Dawn is the author of 2 nonfiction volumes, The Roosevelt Cousins, Growing Up Together, 1882 to 1924, and Freud and Jung, Years of Friendship, Years of Loss. She is also the author of a novel, The Little Balloonist, based on fact about a little French peasant girl who grew up to become Napoleon's official balloonist. Please join me in giving a warm welcome to Michael Salcman and Linda Dawn.
I owe her a kiss, but she's not feeling well tonight, for that wonderful, wonderful introduction. And thank you for your welcome. I want to thank first Helen and Liza Bennett for making it possible for me to speak with you about this subject tonight. The first thing to be said about the brain, I think, is that it was built to make comparisons. Heavier, lighter, faster, slower. And it was Cezanne and the painters in the late 19th century who discovered that a red apple is much redder if there's a green pear near it. And so something as straightforward, supposedly, as color vision turns out to involve the comparative kind of tools that the brain has. Of course, if you want to deal in major comparisons, you have to deal with metaphor, and the master of metaphor is Shakespeare. And in this gorgeous sonnet of Growing Older, he goes ahead and compares the speaker to someone with bare ruined choirs, which are the bare branches of the tree where late the sweet birds sang, in one of the most famous metaphors ever written. And in recent years, it's been discovered that he may have been a Catholic sympathizer, and that this actually has a double meaning, which is the loss of the choirs, both as people and architectural locations, after the time of Henry VIII. Metaphor as a way of thinking, metaphoric thinking down through the ages, the same kind of metaphor, we'll stick with the tree for a moment, can be used in many different ways down through hundreds of years. Eitz Chaim is tree of life in Hebrew, and the tree as a metaphor appears first in the Hebrew Bible. In the 1700s, the classification of organisms was likened to tree branches. In the 19th century, Darwin drew his evolutionary tree in many of his notebooks. And around the birth of the 20th century, the father of modern neuroscience, Ramon y Cajal, likened both the shape and the function of the neuron, the nerve cell that we'll be talking a lot about tonight, to a tree. And you can see that where all the leaves are and is at the top of the tree, and then the output of the neuron comes down the axon, and then even the brushy part at the end, which is in the ground, the roots of the tree can actually touch other trees in that location, as the neuron must send its message to other nerve cells. So what got me interested in all of this was the issue of art and science. We all have a 3.5-pound brain inside our heads. Some of us are scientists, some of us are humanists, and some may be both. And the question was, how does this happen? How does the brain make this happen? The first thing always is to have a good idea, and the first major good idea of my life was to marry Eileen. This past year was our 50th wedding anniversary, and it was very important to marry a very understanding wife. And within 2 years, I was now starting to read contemporary poetry as it was being printed, and and the two of us were collecting art for the first time in our lives, and I was working on the visual cortex of the brain at the NIH. And during that time, I read for the first time one of the 100 most influential books of the 20th century. I read it about 10 years too late, The Two Cultures by C.P. Snow, in which he made two assertions, both of which actually turn out to be wrong. One is that humanists and engineers speak mutually incomprehensible languages. Those were the two cultures. The second assertion was that the communist East would for sure defeat the humanist West because they were producing engineers and we were producing poets. Now, during the daytime at the NIH, I was working on creating new types of floating electrodes. These are little wires that float into the brain so that they float up and down with the pulsations of the brain, and so that in an animal that is free to move its head, isn't bolted in place, is behaving, that you could keep recording from a neuron for many weeks and even months. And we developed some techniques for doing this, and this will come back later on to haunt us. So I was doing that by day, and at night I was writing poetry, and I said, well, I can't be an enemy of either camp. And then all of us have heroes, and some of these heroes are unique scientists like Einstein who actually thought like an artist, or unique artists like arguably the greatest American painter of the 19th century, Thomas Eakins, who did this portrait of a Yale professor who helped invent the spectrophotometer, which is an ancient line on the road to getting to functional MRI scanning. And he carved the frame, and into the frame he carved the equations for the device, and he carved the logarithmic rule. Then there are those unusual people like Leonardo and like Ramon Cajal, and Cajal had a retrospective of his drawings within the last couple of years at the Morgan, who could do both, who could function as important artists and function as important scientists. So this is Cajal with a very primitive microscope drawing the Purkinje cell in the cerebellum, the bouncing part of your brain. This is what it looks like today when you inject it with a beautiful dye. You can see how it resembles a tree. I was briefly involved in a project with Mike and Doug Starn, who are twins, great contemporary photographers for the National Academy of Sciences. They wanted to see pictures of neurons because they wanted to take pictures of trees that would make people think immediately of the neuron. So here the metaphor was two-way and was going in the reverse direction. We also were in a period of time when art, the products of artists, and the products of scientists were starting to look like one another. And here is a wonderful conceptual artist from England, Helen Chadwick, and this is her self-portrait. She's using the brain as a metaphor for the self. Here are beautiful scans, colored scans, showing you a brain tumor and the venous system in the brain, and the arteries. And this is so beautiful that it was actually shown at the world's most important art fair, the Venice Biennale, as a work of art. My favorite example of the conjunction of objects from humanists and from scientists is this. Here is a portrait of a family where the artist, Magnolo Ovalle, from Brazil, has had blood drawn from himself, from his wife, and from their child, and did southern blots of the DNA fragments, and what you're looking at is a portrait done through DNA. So I finally had a chance to write and present a lecture on how the arts and the sciences weren't as far apart as Snow thought they were. And I like to think of a pair of dyads, science and discovery, and art and invention. And just since it'll be important later, this is a nerve cell from a different location within the brain. This is the axon with the information leaving. And you can see all over these filaments are these little dots, which are the contact points between this cell and the fibers from other cells. Those are what Cajal named the synapses. He actually couldn't see them, but he knew they were there. The next thing that happened on the way to metaphor in the brain was that I discovered this paper by Henri Poincaré, a mathematician and engineer in France who set up the entire telephone and telegraph system for the country, who should have won the Nobel Prize and lost the race to relativity theory by just a few months to Einstein. And he wrote perhaps the greatest article, I certainly think it's the greatest article, on creativity and how it worked in the human mind or brain. And he said that there were 3 stages of creative work. You first sit down and very consciously set out to solve a problem. In the second stage, you might be drifting off to sleep, or you might be walking along a beach, and one of the possible solutions comes to you, and those solutions are couched as combinations of ideas, problem and response, call and response in the brain. And he said that the way you pick the correct one, invention is discernment. I mean, that is just a beautiful, beautiful statement. And like many physicists and mathematicians, he felt that a discovery, the most beautiful, the most concise, the most elegant, would be the correct one. And he said the useful combinations are precisely the most beautiful. And 100 years later, a great neuroscientist in England, Zeki, who's written an entire book on the brain and art, put a group of mathematicians, British mathematicians, in the functional MRI scanner. And these mathematicians have been asked to look at a number of mathematical proofs and ask themselves which are beautiful, which are ugly, which are sort of just meh. And it was very reliable, okay? And then what they saw was that for the ones that everybody thought were beautiful, the orbitofrontal area in the brain, which is just above your orbits and just near the olfactory system, as Proust knew it would be, lit up to the greatest degree. And this area had previously been seen to light up when people were listening to music that they loved or looking at beautiful paintings. So, in fact, the first thing we can say about Poincaré's theory is he was right about the importance of beauty, at least as far as mathematics and some forms of art are concerned. The year I was born, Robert Frost wrote many wonderful essays on how to write poetry, and he gave the best definition of metaphor I know. There are many other things I've found myself saying about poetry, but the chiefest of these is that it is metaphor, saying one thing and meaning another, saying one thing in terms of another, the pleasure of ulteriority, which he meant the subconscious, the buried, the deep, would come out in the metaphor. And then he put on his aw shucks New England kind of act, that he was just an innocent farmer, So also is philosophy, and science too, for that matter, if it will take the soft impeachment from a friend. So the brain has two incredible advantages over any ordinary machine that we can build. One is the way the brain has so many moving parts, the brain in numbers. And the other thing that's important about it is the amount of association cortex in the brain that we don't ordinarily think is doing anything. And I'm going to show you how much it does. So here's another one of Ramon Cajal's beautiful drawings without a modern microscope around 1890. And here we're blowing that area up, and with a modern electron microscope, you can see the synaptic contact between two cells. This is just 100 micrometers. It's about a tenth of a micron, or about 10 to the minus 7th meters. And very, very small, but it is clearly a separation across which the electrochemical changes occur that communicate one neuron with another. As we go up the animal system, the animal tree, the number of neurons in the brain increases tremendously. The ant brain has about 10,000, and that ant builds cities and carries objects 10 times its weight. The frog has 1.6 million neurons. The human brain has about 1 trillion neurons, either 10 to the 11th or 10 to the 12th, depending on whose paper you read. And the number of synapses per cell, connections from other cells in the brain, is about 10,000. So for those of you who remember scientific notation, each of these numbers is simply 1 followed by the number of zeros that is in the exponent. So you can see that 1 million is 10 to the 6th. It's a 1 followed by 6 zeros. And so if we simply add the exponents, the 10 to the 4th and the 10 to the 16th, the 10 to the 12th, we get a total number of synapses that's 10 to the 16th. It's also possible to use statistical theory and figure out how many possible non-trivial connections there are in such a brain, and there are 10 to the 22nd. So in pre-Hubble era, we thought that there were 10 to the 10th galaxies in the universe and 10 to the 10th stars per galaxy, for a total of 10 to the 20th stars in the universe. That number now is considerably larger since Hubble. But at that point in time, it was true that each of us in this room has more connections than visible stars in the universe prior to Hubble. How prescient was William Blake with this incredible series of metaphors: to see a world in a grain of sand and heaven in a wildflower, hold infinity in the palm of your hand and eternity in an hour. And this was discovered in one of his notebooks long after he was gone, and it will not surprise you that, in fact, we can count the number of grains in all the beaches of the world and all of the deserts. And when you look at the number of grains, it's 7.5 times 10 to the 18th. And so that means that there are more connections, unique connections in your brain, than there are grains of sand on the planet. And 1 grain of sand is about a cubic millimeter. And if we look at a cubic millimeter of brain, the number of neurons in that cubic millimeter is 100,000. The number of axons exiting neurons, because exiting filaments, because those filaments, remember, they're going ones crossing that space that didn't come from a neuron in that space. There are 2 million. And the synapses in a grain, a piece of the brain the size of a grain of sand, well, you can see there are 1 billion synapses. There is more information that is produced by your brain, bytes of information in a year, in something called petabytes, which puts you out to 10 to the 15 times 300,000. And there is, in the most complicated machine that human beings have ever built, the Hadron Collider in Geneva. So a long time ago, I decided the probability theory would be very important in understanding the brain, because this is the way we handle large numbers. It's kind of like fancy statistics. In this case, you can see a fake normal distribution here where the distribution is changing over time, and that's what we mean by a stochastic process. And an individual neuron might have all of this mathematics attached to it. So an engineer and mathematician approached me about those floating electrodes, and we discovered a way, using a lot of math, to figure out when a cat was looking at something it was really interested in by recording from different cells in different neighboring parts of the visual cortex. And we came up with a correlation function that we thought we would call surprise. So let's talk a little bit about the associative brain. 80% of this brain, look at the purple areas, is association cortex. It's what in the old days when people said, oh, we don't know what 90% of the brain does, or 90% of the brain isn't doing anything. Those are all wrong comments. 80% of the brain is what we call association cortex. It's there to massage and further analyze the incoming data that is coming into the brain along a limited number of pathways. There are relatively few things in the brain that have really defined territory. The visual area, the motor system, the primary sensory system. And we're going to talk a lot about the angular gyrus, which I used to tell residents was the dictionary of the brain. It may be even more than that. So the percentage increases with the size of the brain and increases with species. This is from when I had a real day job, and I'm clipping an aneurysm here. This is the carotid artery, and this is the optic nerve, which has 1 million input fibers to the brain. So the two optic nerves together have 2 million fibers. The total for the whole body, all the spinal nerves, all the cranial nerves, is 6 million fibers. So that means that vision represents 1/3 of all the inputs to the brain. So images are very important, whether these images come by words or they come by direct visualization. And so Zecchi discovered in the 90s and propounded the theory that we don't have one visual system, we have 5 or 6 visual systems. And here is the primary system where the information from the optic nerves eventually ends up in raw fashion. And then I don't have a small enough thumb to do this. I don't really know how to do that with my phone either. And here are the primary association areas. But under the temporal lobe, that part of the brain that's inside the part of the skull next to your ear, and that has memory systems built into it, underside of the temporal lobe has areas for color analysis, for facial recognition, and for counting objects. And then on the outside of the brain, near the parietal lobe, and I'm almost always showing you the left side of the brain, and you can see here that area, and that's movement. So there's the movement of the animal in the jungle that we have to spot, there's the color of the animal, and there's the shape of the animal. Now, another wonderful investigator in this area is the neuropsychologist Ramachandran at UC San Diego. And he did a study where he looked at a group of patients who had all strokes in the angular gyrus and who could not interpret metaphors and who thought of everything concretely rather than philosophically or literally. And so he came up with the idea that the angular gyrus was the place where metaphors were decoded. As you will see, it is also the place where metaphors are constructed. So here we've got a drawing with the angular gyrus sitting there, and we've got the hearing and speech area just in front of it. We've got just above it some of the secondary sensory areas for the body surface, and vision is just behind it and inferior to it. It kind of sits in the center of all of these areas that probably want to talk to one another. So we talked about how important beauty is in Poincaré's theory, but even more important was this idea of combinations that the brain needs to go through. It needs to throw up the combinations, and then it needs to resolve which is the correct combination. And now we have an answer for that. And today, cognitive neuroscientists more often look at networks than they do individual parcels of land in the brain. And two of the major networks, the executive control network, which is the network that links together a bunch of places when you are sitting down to do your house budget. That's what you're using, and you're fully conscious. When you are sort of drifting off to sleep or walking along that beach and solving equations with Poincaré, you are using the default network, which is about spontaneous cognition, not cognition that you've kind of ordered into existence. Notice that one of the pieces in this network is the left angular gyrus. It turns out that when you test people in the MRI scanner for their ability to manufacture metaphors, so if they say the lamp is glaring, they might come up with a literal synonym for this. But if it's really bright, they might say it's a supernova. And so it is possible to see what lights up in the brain when you are doing synonyms or when you are doing metaphors. And then they subtracted the synonym, you know what I'm talking about, values from the values with true metaphors and got this very complicated map. And because I was invited to give this talk, I came up with a new visual metaphor, which is the airline map, right? And so what you're looking at really is nodes that then irradiate a wide variety of places in the brain. That these active nodes are very important to the kind of work you're studying, and they irradiate all these other places, and some of those places might then re-irradiate in other directions in the brain. And if we thought of the front of the brain as the East Coast, of course, and the back of the brain the West Coast, that's how you could get from one extreme area in the brain to another and might have a way of getting some really wild, interesting metaphors going. The fun thing is, I showed you just a moment ago this area on the outer surface of the brain that decodes movement of body parts. It also lets you know about the position of the body parts in space. And you may not realize that we have a lot of metaphors: shouldering responsibility, footing the bill, twisting my arm. Okay? And when people in an MRI scanner say those metaphors or think about them, the area where the body is looked at positionally in space lights up to an extreme degree because now it's added the metaphoric implication of the movement or the location. Now, they subtracted a lot of the stuff so that we could actually think about it. Here are all the important nodes that the angular gyrus contacts. And you'll notice that here is the right hemisphere. We're looking at it from the side. The scale is each one of these is 2.4 seconds, and then it switches over to the left side of the brain. And it really is like those other visual metaphors that I'm fond of, whales. It's like whales trying to communicate with one another across an ocean. If you scaled up the size of a whale, or scaled it down to a neuron and scaled the oceans down to the size of the brain, I bet it wouldn't be too far different. So they're communicating across great distances. Our neurons communicate across great distances. There's a wonderful book on how observers, us, since I don't know how many painters are in the audience right now, artists are in the audience, when we are looking at an artwork, Here's the primary visual system again, going forward into the two major directions, going into this area here where there's color and facial recognition and numbers and so forth. When we look at an artwork, eventually that information reaches the prefrontal cortex here in your frontal lobe. This is the tip of the temporal lobe. And then depending probably on your experience with looking at art, the books that you've read, the amount of art that you've seen, and it could be literary art, right? We're still using the visual cortex as part of that system to decode what we're looking at on the page. The frontal lobe then is going to modify what we simply saw initially. And it really is true what Duchamp said, which is that the observer completes the artwork. Now, I love this. I'm going to take a little bit of time to tell you about this, because in the internal battle between prose and poetry, we now have information to declare a winner. This is an MRI scan, and the left side is up there. And the front is away from me. It's over here. And here are the occipital lobes, and you can see how brightly they are lit. And again, a group in England, and the paper, I love the fact that the paper's called By Heart. You'll hear why. They took a group of English professors and graduate students into the MRI scans, and they read them prose and took the MRIs to see how much the brain lit up when you were reading prose. They took a group of poems that had been selected by the investigator and did the same thing, which gave an intermediate score on the MRI. And then they asked people to read a poem or recite a poem that they loved, a poem that they knew by heart. And those poems lit up the brain to the greatest degree, between prose and the poetry of two types. And what we're looking at here are the temporal lobes lighting up, more on the left than on the right in this case, and a part of the basal ganglia here, which seems to be connected to an emotional network. And if you look at the data, you can actually see how the ratings of those different types of literature linked up with the scores on the MRI scans. So my first conclusion is that Frost was right, even with a mild or soft impeachment from him, that not only is art and poetry simply metaphor, to a large degree, philosophy is metaphor, and we can almost not give a scientific lecture without talking in terms of metaphors. Probably only numbers for the mathematicians have some sort of limit on the importance of metaphor there. So I would conclude that poetry and painting both depend on metaphor, whether actual or verbal or an image that one sees, and that a lot of the metaphors involved are based on image rather than other sensory inputs. I'm going to close with this bit of wisdom given to me by Philip Glass, and it was given to him by Leonard Bernstein. An artist needs two things in life: a good idea and too little time. And I've run out of my time now.
Thank you, Michael. That was
It's my pleasure.
Wonderful. I'll never feel the same way about my brain again. I am now in awe of mine and everyone's, and mostly yours. Thank you. Now, you write in metaphor making, the activity of neurons in the brain is capable of generating many possibilities and choosing among them.
Yes.
And also that neurons are capable of connecting at long distances within the brain to call up the most unusual combinations. Does this brain-wide communication mean that the classic right brain, left brain dichotomy no longer holds?
Well, I think I never believed that it held at all. I thought that was really a product of daytime television. And I'll just give you my number one reason for why it can't be true, which is that the right side of your brain controls the left leg and the left arm, and it controls the left half of visual space, and all the information that it needs to do those things come into it. And your left brain, it's really like having two brains. Your left brain controls the right side of everything. And so to say that one side of the brain is emotional and one side of the brain isn't and is all about hard calculations. And the kind of data we get from functional MRI that's in the literature, it has all sorts of issues with it. Things aren't hard and fast. This is why people have stopped looking at individual areas but are looking at these networks. I can't swear to you that when a message starts in the angular gyrus, always on the left side of the brain, it is going to reach all those other areas. We're not sure those areas are connected. All we know is that they all light up when a certain task is given, and they light up for a wide variety of reasons that can change the amount of blood flow or blood volume in that area. We can't be that certain about the data, but it's the best data that we have right now. The thing that definitely makes the two hemispheres different is that almost all language function is in the left hemisphere. And you saw in some of the examples I gave you at too quick a pace. I'm sure some of them started in the right hemisphere, but eventually both hemispheres were involved. Some started in the left, and both hemispheres were involved. And a thing that I neglected to say was that those two systems, where I said that one system would hand off to the other and then it would come back to go from conscious to semi-conscious to conscious work again. It turns out that in the making of metaphors, both systems are engaged at a certain point in the process. It needs everything. Everything it's got. It's using everything it's got to create all of those combinations. So I don't think, except for language, and there's some, and I can't find the paper again, but it says that in birds, the song center is usually in the left hemisphere. And 2/3 or 3/4 of left-handers, instead of having language on the right side, they still have it in the left hemisphere. A lot of it is pre-wired.
You quote Nietzsche as saying that the drive to form metaphors is man's fundamental instinct. Ordinarily, we think of metaphor making as confined to literature, but clearly that's not the case. Can you tell us more about how critical metaphor making is to our thinking? Why Nietzsche was convinced that our basic instinct is to form metaphors?
Well, I don't know. That's actually coming from something else that I wrote. I center everything that I had in my library. But I don't know on what basis Nietzsche came up with that. I have never, to first-year medical students talking about the neuron, have never in my lifetime not started out by standing up and saying, you know, all those leaves in the tree, those will stand for the synapses, and they're on branches that are the dendrites coming out of the neuron in that direction, and then the information goes down the axon, the trunk of the tree, and it ends up in those other filaments, which are the roots of the tree. I mean, how do I introduce them to the subject? And people still show them in classrooms Cahal's drawings, because certainly as drawings they've never been equaled. Right. I don't know how to talk about most things without using metaphor. Now, maybe it's just me because I write a lot, but I bet most of you have that same issue if you look at it really closely and honestly. And that's why I gave you examples of visual metaphors. I wanted you to see that we do that stuff just all the time without even thinking that it's a metaphor, but it is. And I'm using the term metaphor as opposed to saying and simile and analogy and all sorts of other things. These are all types of comparisons. And the more out of the world they are, then they become Blake or Shakespearean, or Emily Dickinson type metaphors.
I did ask Michael if he could give us a little advice on how we could get a little closer to a kind of Shakespearean metaphor, if there was something medically, physically in our brain that could help us, but he did not offer anything.
I don't think there's anything practical from a medical point of view. I think keeping a notebook at your bedside on your night table, and the thoughts that come to you while you're reading somebody else's work. There's a nice saying that for every poem you write, you should read 100 poems by other people. And, and that writing is rewriting, right? So, and that will all influence the final outcome. So you're drowsy, you're thinking about other things. A word or a phrase that you're reading or you've just thought up may come to you, and it may be the kernel, it may be the seed of work that's really outside of your daily use of language that is really extraordinary. So that's one way you can influence it. I suppose for visual metaphors, there are all sorts of medications, most of them semi, hemi, demi, illegal, that you can take and that change what you think you're seeing. And I don't know that this has ever really been looked at, but other than that, I really don't have any. It's not like going to the gym.
You have referred to Poincaré and his model of how we create. Could you tell us more how it corresponds with your physical model, and did his model help you with your research? Were there any kind of...
Well, the research that I showed you is not mine.
Okay.
So I've tried to put all these things together and to flood you with a lot of functional MRIs because they're pretty pictures, and also it's the technique that supplanted the electrotechnique that I worked on. So with the electrotechnique, you get a lot of information out of very few cells for a long period of time. With the functional MRI scanner, you don't have a lot of time to look at something, but you can look at large areas of neurons to see how active they are. So it's a very different type of information. Mm-hmm. I think the major thing when I came across this paper was a consortium of scientists that was led by Harvard, and it just came out a couple of years ago. And I said, God, there are the two areas that he was interested in, the conscious solving, mm-hmm. the semi-conscious solving, what some art critics call dreaming while awake. So it fits perfectly.
It does.
And then it's very cool that they both become active at a certain point as people struggle to create a really innovative metaphor. And in fact, they fought with some of their subjects during they only had it for 10 seconds. That was the whole data gathering time. And if they created a metaphor, and they would say, can you do better than that? And then they used the score of the most powerful or interesting metaphor that they could find because the furthest away from being just a synonym.
Do we want to ask, does anyone have a question? Ben?
I'm curious about paradoxical pleasure I'm curious about the paradoxical pleasure that works of art that are tragic give. Oedipus blinding himself, or King Lear on the heath. These are things that would give no pleasure at all in real life, but do give pleasure when seen on the stage. And I wonder if you can make a neurological comment.
No, not one that's sensible, or one that we have data on. Here's the problem. We don't know in a lot of people who enjoy something that's grim. Just yesterday, Eileen and I saw 1917. What a phenomenal motion picture, and we greatly enjoyed it, but we were stressed out. And it's not that the areas I've showed you that light up are areas that are pleasure areas. With the possible at the end with poetry, I showed you a caudate nucleus that might have something to do with pleasure. But by and large, the areas are not involved with pleasure. They are involved with a concept of beauty. And to people who see Guernica, they don't see the horror of the painting. They feel the painting is beautiful. It's impressive, it's special, so that we don't know enough about what just beauty does to the brain, I think, to answer your question.
You spoke about poetry, literature, and, of course, being a comparison and all that, and what that does to the brain. What does music do?
Well, in fact, I showed you, it just flew by, I know. I showed you the orbitofrontal area in the mathematicians in Zecchi's first important experiment that looked like they were getting pleasure from mathematics, from elegant proofs. And what I mentioned was that that area also lights up when people listen to symphonic music that they're crazy about, and lights up when they're looking at a painting that they're crazy about. And that's pretty much what I know about it. There are some issues involved with the parietal lobe. There are some issues with the areas that you can see light up on functional MRI scans in people who have, for example, violinists who've spent hours practicing. You can see that the anatomical region has gotten larger than it is in the average person, and that it lights up more strongly. But I don't know in detail what those areas are. And it's sketchy, partial data, based on very few people who've put in the MRI scanner who fit the criteria. But, we're going to know more and more about this as the decades roll by. Well, yes and no. The question was that when somebody has a damage to the brain, that there's a certain amount of plasticity in the brain that allows other parts to take over. And it really depends very much on whether it's a function that both brains are involved with, so that the other brain can take over a little bit, how much of the area has been destroyed, because if it's really critical to that function and all of it has been destroyed, that's not going to work out as well. And it depends on whether you're talking about psychology as opposed to physiology, in the sense that people who lose sight or hearing have always been said to make up for that deficit. They get around the world by using the other input in place of it. And, that's just human beings are very good at learning, and that's how they get around it. Now, there is true plasticity in the brain. When you learn something, and this gets back to those violinists, when you learn something, and maybe in rehab, to the point that he was making, you can actually have synaptic contacts grow sturdier and approach their target that they didn't originally before. And that is a degree of microscopic plasticity that definitely occurs in the brain. And it occurs in certain parts of the brain that are very good at doing this, like the hippocampus, the memory area in the temporal lobe, and the layers of cells that form the ventricular system, the ependymal lining. Those areas can spout new neurons, can help make new connections. But it's so dramatic when somebody does better that it has sort of flooded everybody's idea. You know, it's kind of like Van Gogh selling only 2 paintings while he was alive. Well, that's not what happens to most artists. And Van Gogh's brother was his art dealer. So there was no lack of PR, you know. It's just the average human being couldn't deal with what they were seeing on the canvas. It wasn't beautiful for them yet. So the plasticity thing, yes, it's there. And sometimes, no, it isn't.
Early on, you referenced C.P. Snow and the two cultures.
Yes.
And I think I quote correctly Nabokov, who said it's a dimple of a ditch that a small frog could straddle. And I wonder whether you think that ditch has enlarged or contracted of late, and how, given your lecture and your suggestion that the two might be linked, we might proceed to profit from a scientific comprehension of metaphor making.
Well, that's a beautiful question, beautifully stated. There is a lot that might be done in the future about that. I think the first thing that's very important to do is to detoxify the positions that scientists take and that artists take. You know, the great American artists, the abstract expressionists, hated engineers and scientists because they blamed them for the atomic bomb. And then you have paintings that actually imitate atomic bombs. And scientists are always thinking that artists really don't think. Of course, an artist who doesn't think is not a very good artist. So I think the first thing is, in the two cultures, to make them all agree that, yes, they have the same amazing 3.5-pound object. There have been philosophic studies done on personal characteristics in the two groups. They reason by the same techniques. They have the same degree of all sorts of other personal characteristics. There was a whole issue of Daedalus that was devoted to that years ago. So, you know, there's great hope if people will allow one another to hope. And there are artists at times and scientists who've actually linked. Bob Rauschenberg had a team of engineers with whom, for several years, they created artworks that were on the border between the two fields. And I have a much larger library that I didn't have the time to show you of artworks and science works approaching one another and looking like one another. And that's really the tip-off, because technology drives art at the same time that it drives science. And as soon as somebody has their hands on the technology, they start making things that resemble what the other group is making. So,
Maybe two more questions.
Am I on? Yeah. I know you're a major collector of artwork, and my question is that, and you mentioned abstract expressionism, which I suppose is a major metaphorical visual art, and that it's not realistic. In the last several years, narrative art has become more predominant in the art world. I'm wondering what your feeling is about that the narrative is not as metaphorical as, say, abstract expressionists at this point.
Oh, narrative art is often more metaphorical than abstract art. The great advantage that abstract art has for people who are sympathetic to it and love it is that it throws your thinking as you look at the art back upon yourself. You interrogate yourself rather than just interrogating society or some other issue as you would with a work of art that is more realistic, more representational. But there are a tremendous number of important representational artists working today, and there wasn't a bigger advocate for abstract art than Clement Greenberg was, and I had the pleasure of touring around a show, just the two of us, once, and he reemphasized something that he'd written about, that he would gladly support a realistic artist who was as good as Vermeer or Velázquez if we had one. Okay? But there are ones that are very important today, and I think they're equally metaphoric. It's a different kind of metaphor.
Boy, thank you so much for doing this, and I hope you didn't deal with this in the first 5 minutes because I missed those minutes. I'd heard that what we see, that maybe 10% of it comes through the eye and 90% or 80% or some large number is provided then by the brain, and then we call it what we see. Is there anything to that?
No, but I'm so glad that you asked the question. I have two types of answers, right? Short ones and more detailed ones. And I'm so glad, because I didn't have time to show a slide like this, that vision is a miracle and the brain is a miracle. Because we have a lens, we are walking around in a world where left and right are reversed and up and down are reversed. And the brain, through the optic chiasm and other parts of the visual system, turns everything right side up, and left and right now are correct. And even more amazing, this is a theory of Zecchi's, is that, now that we know there are those different visual systems, well, it turns out they have different numbers of synapses in them, and they have fibers that are of different lengths. And so we don't see the lion's color in the jungle, or his shape, or his movement at the same time, but for the brain, which it's like working on film. All of those delays for 2 out of those 3 systems are corrected so that you see the lion as a single entity. And his theory, everything until this point I'm fine with, but his theory is that the function of consciousness is to reframe when all those signals arrive in the brain.
Wow.
Please join me in thanking Michael Salcman and Linda Dawn for an unforgettable.
Wonderful.